All right, hey guys. My name is Eric Bridgeford, and I'm going to be discussing a high-throughput pipeline that we designed for the identification of robust connectomes. So over the past decade, multimodal MRI, or M3R as we call it, has become increasingly common. M3R includes diffusion MRI, which is measuring the movement of water throughout the brain, fMRI, which is measuring the dynamic brain activity, structural MRI, which provides high-resolution anatomical images. So in connectomics, what we're concerned with is taking these raw data and using them to produce multimodal networks of brain connectivity. So presently, there are many open-access M3R datasets, including the Consortium for Reliability and Reproducibility, the Human Connectome Project, and the Healthy Brain Network, to name a few. So despite the fact that fMRI and diffusion MRI have been around for decades, with millions of dollars invested in research, there are still no biomarkers generally as standard practice for clinical psychiatry. So what might some of the reasons for this be? So the processing and analysis to obtain connectomes is challenging. The sample size of single studies is often small, usually on the order of tens to hundreds, as opposed to the number of features of a connectome, which is often on the order of thousands. So the data often exhibits heterogeneities within and across studies. The existing pipelines that are often encouraging researchers to sort of hot swap algorithms per data set. So in this process, they'll run the pipeline on the data set, figure out which algorithms work best within that particular data set, and then swap out the parameters every time they run it. And finally, there's a lack of generative statistical models for connectomes. And this makes quality inference quite difficult. And so these inconsistencies sort of combine to lead to a failure of replication across studies, across sites, and across investigations within the field of connectomics. So we decided to start development of our pipeline by designing principles that we could use to evaluate existing pipelines in the MRI community. We broke these up into three chief categories, which were the statistical principles, which focus on whether or not the tool is statistically valid. Is it accurate? Is it reliable? And is it robust? We have computational principles. Can other people use it efficiently? Is it expedient? Does it scale? Can it be ported to different platforms? Does it require user configuration? And can it be used open access? And then finally, we have the connectome principles. Is it multimodal? Will it process diffusion and functional connectomes? And can it produce the usable connectomes directly from raw data, which is really what we need? So what did we do with our pipeline, which we called Nutmeg, or NDMG, as you can see there? So the Nutmeg pipeline takes raw M3R images and produces connectomes for downstream analysis. Nutmeg leverages standard tools for each operation across all modalities, and the analysis process occurs in parallel, and it can be massively parallelized on cloud architecture. So the Nutmeg pipeline has been used to process data from over 25 different studies consisting of about 6,000 scans. To quantify its reliability, we developed the discriminability statistic. So discriminability, in a quick rundown, is a generalization of the interclass correlation coefficient. However, it's a non-parametric generalization, whereas the ICC is assuming the data is Gaussian. So this makes it robust when the data can't be effectively summarized by a Gaussian distribution, which is often the case in real data and turned out to be the case in the actual connectomes themselves. So the statistic is the probability that the observations, which were in this case connectomes, within the same subject were more similar to one another than the connectomes across subjects. So as you can see in the figure to the right, these are the discriminability scores for the diffusion MRI and the functional MRI across 25 different scanning sites. So as you can see, the pipeline achieves a discriminability score over 0.8 for all of the studies, and it's nearly perfect for the diffusion MRI studies. So the next thing that we went down was a multiple group level analysis, or what we call a mega-analysis. So in this case, we have 6,000 connectomes across 25 sites. So we're seeking to effectively identify which patterns were consistent across nearly all of the connectomes within a particular cohort. So what we're going to focus on here is the diffusion connectomes. So for the diffusion connectomes, on the left, we're looking at the average diffusion connectome across several thousand different individual diffusion MRI scans. And so the immediate thing that jumps out is that the ipsilateral connectivity, which is the connectivity within a particular hemisphere, which are the red and the blue edges, tends to exceed the connectivity across hemisphere, or contralaterally, which is indicated by the green edges. And so what we found when we applied this model at the individual connectome level, which you can see in the right plot, so what we're looking at here is the individual diffusion connectomes. Specifically, each line is indicating the distribution of the magnitude of the difference between the ipsilateral and the contralateral connectivity. So a value greater than 0 indicates that the ipsilateral connectivity exceeds the contralateral connectivity. And as you can see with the little red line, which is the diffusion MRI here, these are each of the individual studies. This tends to be the case, and in fact it's the case in 100% of the diffusion connectomes. And the difference is significant in 99.9% of the diffusion connectomes at the 0.05 significance level. So the next thing that we realized was that the magnitude of these effects for this property that's present in all of the connectomes varies incredibly widely across the different studies. So in this figure, each line shows the distribution of the magnitude of the difference, again, except we've broken it out by study. And as you can see, both within and across studies, there's a lot of variation here. So to statistically evaluate the magnitude of this sort of heterogeneity that we found, we developed techniques that allow us to effectively compare different cohorts conditioned on different properties. So as you can see in the blue, this is not conditioning on anything, and what we found was that there was effectively a significant batch effect in 60% of our comparisons. When we attempted to correct for some simple demographic things such as gender, correcting for age differences between the different scanning sites, and different ethnicities that could potentially be present, this failed to mitigate the sort of presence of this batch effect. So how can we use Nutmeg in the future going forward? So Nutmeg serves as an efficient pipeline for scalable connectomics. Everything we developed is open source. I'm actually giving a talk in 3 days in the Open Science Room that you guys are all welcome to come to, of course, and we'll delve directly into the code. The pipeline can be massively parallelized on Amazon Web Services, requiring about an hour per scan. We're compliant with many best practice community standards, such as Docker, Singularity, and BIDS. We have thousands of process connectomes already available online at our website, and we've prepared an extensive quality assurance suite produced with each connectome. So finally, Nutmeg establishes a need for improving cross-site replicability in connectomics investigation. So the Nutmeg pipeline proved highly discriminable within each of the 25 different studies that we had across 6,000 different connectomes. Using the results of the pipeline, we were able to identify properties for both functional and diffusion connectomes that were reliably present in effectively all of the connectomes for each of the studies and modalities. The magnitudes of these properties showed substantial heterogeneity, particularly within and across studies. And finally, attempting to correct on the basis of demographic variables and a number of other factors that are covered in my poster, which I'll be doing on Tuesday through Thursday, failed to mitigate the heterogeneity that we had observed. So what are our next steps? So in the future, we're going to be focusing a lot of our attention on how we can better quantify and mitigate these batch effects related to these different effects and confounds. So first, we can use some better analysis methods. So for our diffusion pipeline, we used deterministic tractography. In the future, we might look at how probabilistic tractography, which carries a substantial computational cost compared to the deterministic tractography, can improve or worsen the batch-related phenomena. So the next thing that we're interested in is, can we do multi-scale inference, and how can we use multi-scale inference? So this would be using various parcellation schemes and sort of combining them into one cohesive network representation. What can we learn there? Can we mitigate batch effects that way? So the second question is, how can we make the data itself better? Can we obtain deeper phenotypic data for each individual? Can we better harmonize the cross-site investigations to estimate connectomes robust to these types of confounds? So I wanted to give you guys all of the links associated with this particular work as well. And I wanted to thank all of my collaborators and the funding that we're receiving, particularly my PI, Josh Vogelstein, and a PhD student who's been a substantial mentor to me, which is Gregory Kiar.